So why on earth would you consider geoengineering? It sounds scary, right? How many of you have heard of geoengineering? How many of you think it's a good idea? Yeah, right. Okay. Me too, carefully. So mitigation is all the things we know we need to do. Conserve, have energy efficiency, transition to solar, all of those things we know we need to do. The trouble with it, and why I got into this sort of Band-Aid option myself, was the thought that this was not going to happen in time to prevent great harms. And so that's why I'm in it, at least. And when you have that mindset, you want to make sure what you do is reversible, harmless and reversible. Adaptation are the sorts of things if we're going to build higher walls around our cities. We're going to make sure that our sanitation facilities come out above water rather than below water, things like that. And this is a current reality in city planning. So geoengineering, in my view, is just this series of planetary Band-Aids to buy time. It's a possible emergency backup. When I started this work, it was with the feeling, I hope this is the backup option I hope we never need. Well, it turns out it looks like we're going to need backup options like this. It's trying to buy time for all those things we know we need to do. But there are people who are really concerned about the moral hazard. And then what does that mean? That means that if you think, well, we can fix it, the engineers will figure it out, and we can just keep on with our 10 miles per gallon car and burn the lights all night. Well, no. There is no really good techno fix. And so if you're getting into geoengineering, don't make that assumption that you're going to fix the root problem. You're not. You've got to fix the root problem. You're just giving people time to do that. Make sure you first do no harm. Make sure it's localized so you understand the effects. You don't suddenly do something worldwide that you don't understand how to undo, and have an undo plan. Because the history of humanity is that there's always some unintended consequence. So here is something called the greenhouse gamble. How many of you have seen this? Okay, this is a lovely slide. If you go to this website, this is about how bad is it going to get. And this is highlighting with policy and without policy options. When I first saw it, the without policy option looked a lot like the with policy option. It's a way to present probability wedges. So if you said that you want to go over and spin this wheel of fortune here and click on it, the chances are good, right? They're less than half that you will end up less than 5 degrees C temperature rise without policy. That's a horrifying thought. The chances are very good that you will end up above 5 degrees C, maybe above 7 degrees C, temperature rise by 2100, if we don't change anything. Even if we put in the policies that they're advising, the chances are still sort of almost half that we're going to end up above 2 degrees C temperature rise. Why do we care? We care because there are a host of impacts for every single degree that we increase. There are terrible impacts. You probably can't read these very well, but this was a brilliant graphic that Terry Root, used to be a professor here, in climate change, pressures on species was one of her specialties, part of the IPCC, the Intergovernmental Panel on Climate Change. And she worked with a graphic artist to make some of the 2007 assessment conclusions accessible as a graphic, as a visual that we can see. This is worth drinking in. So the difference between rising 1 degree C, 2 degrees C, and 5 degrees C is all the difference in the world. For instance, increased risk of extinction for 20 to 30% of known species with 2 degrees C rise versus extinction, not even risk, extinction of more than 40% of known species. Our web of life disappearing around us. So there's a reason why you really fear if you're going to get up in this very high region. There's enough problems if you're down here. Why is this happening? It's happening basically because we sort of changed the stable equilibrium set point, if you will, of what the temperature of our atmosphere is as we're changing its composition. So we have this balance, as we always have, between incoming energy and outgoing energy, but we've changed what that stable set point is. If we had no atmosphere at all, we'd be like the moon, right? Very different set point. So we've changed the composition of our atmosphere. There are all kinds of things that you can look at, I forget if this goes live, I guess not. If you look up these slides later by viewing the, I guess I'll put the slides on the coursework site too, so you can look at them and look up these sources. You can play with these yourself, and what you get to do is start clicking on how much of this effect is land use or ozone or aerosols or greenhouse gases, so that you can see what, in the best assessment of climate scientists, what is it that's causing this? We are out of bounds now. We are running an experiment that hasn't been run. We're in conditions that haven't been seen on Earth in at least the last 800,000 years. This is from John Koomey's book, where we're just way out of sight on CO2. And the no policy cases for greenhouse gas concentrations, it's going to be big. And there are other gases to worry about too. Methane actually is worse than CO2, per molecule. And there's no end in sight. And this thing is saying, this is the MIT no policy case, the 5 degrees C. So this is a Copenhagen 2009 diagnosis. Oh, and so the 5th assessment report had even more from the IPCC, which is about 2,000 climate scientists around the world, a UN-appointed body trying to figure out what all this means. I mean, you can hardly get a more impartial and more biased towards conservative statements body of scientists than this group. And what you're seeing is CO2 going up, summer sea ice extent going down, ocean heat content going up, sea level rise is happening. Where's the good news here? The projections here, global mean sea level rise, depending what model you have. You have some ironies here. Back in the old days, 1962, one of the big oil companies was advertising that they supply enough energy to melt 7 million tons of glacier. This was a really powerful statement. They were proud of this. It turns out that for once, advertisements didn't lie. These are the sorts of costs that people were estimating a couple years ago for, just a few coastal cities. I didn't want to swamp you with all of them, but per year, New York City is spending $2 billion per year to fend off rising sea level effects on its very, water-oriented city. Now, this is an exaggeration so far, right? Graphic artists have their fun. Also have their fun. This didn't happen yet. And then there are really fascinating things like, how does the US generate its electricity? You can see there are changes. There are rays of hope for sure, but it becomes really interesting. So this is coal, natural gas, oil, again, you can look at the slides after I put them on our site. And that there's no CO2 techno fix is this particular story's headline, because we have other things happening too. Besides CO2 in the atmosphere, we have CO2 in the oceans, and it's certainly not helping ocean health at all. And then there's the whole contention, climate scientists seem pretty sure about this, that because we have melted so much ice in the Arctic, we've actually destabilized what was historically a very low temperature sort of anchor point to the rest of climate, so that the jet stream has now gotten destabilized. So if there's any sort of perturbation, oh, it jumped ahead for me, you can have terrific weather changes and terrific storms, more and more intense storms with horrible human costs. So, it's not great. We're in hottest summers, coldest winters, heat and drought, fish dying, desperate options being taken to conserve water, and pressure on all the rest of the species that share this planet with us. These are slides from Terry Root about just how difficult it is for species. If you're pressured because it's too hot here and you need to migrate where your food is, well, you may be encountering a new predator. I mean, it's part of what drives, when climate change is driving change like this, part of what drives species extinct. And so it's just, we've gone from what used to be less than one species in over 1,000 years dying, to what is now about 1 in 10. So less than 1 in 1,000 to 1 in 10. So we are in the beginning of the sixth wave of extinction. So not so good. So, Calvin and Hobbes are getting rather discouraged. You're packing. Yep, get your toothbrush, Hobbes, we're out of here. It's an outrage how grown-ups have polluted the earth. I refuse to inherit a spoiled planet. I'm leaving. Really? Where to? And that is the question, right? We're not there yet. So again, the slide I showed you before, that's why you would consider geoengineering. But it has these horribly complex issues, possible unintended consequences, possible irreversibility for some of the options. And of course, who governs it? That's one of the big mysteries that Armand and I run into. Who decides once you develop this? And doing nothing, you know, that's what we got. Well, there's a lot, right? There's huge wildfires right now in our neighborhood. And there are many, many ideas. People have many, many ideas, all looking at what the Earth's energy balance is and what we can do about it. More proposals. I mean, you will find more and more. They tend to sort out in a couple of different things. Attempts to control long-wave or short-wave radiation, attempts to do surface modifications, some of us. So two distinct strategies, the way some people sort it out. One of the most common kinds of geoengineering you'll hear about is the kind where people are trying to mimic what volcanoes do. And so many people, when you hear geoengineering, are thinking about this. And this was the idea to put stratospheric sulfate aerosols originally. Now they're moving on to other kinds of aerosols in the atmosphere to mimic what's been observed, that when volcanoes erupt, you end up getting temperature suppression, which is interesting. It's like, oh, okay, there's our heat shield. Why don't we just do that? And this is an option that many people are studying seriously, but they're finding more and more, thank goodness they're studying it, so you don't just suddenly adopt it when your backs are to the wall without studying it, because there are some real consequences. It changes rainfall patterns. It changes where droughts will be. It actually, when you turn it on, you could suddenly, this is a courtesy of Ken Caldera, who is a big and very credible advocate for let's at least study what's happening here so we don't just adopt it, you know, foolishly without knowing what we're getting into. And if you do this, you can drop temperatures pretty quickly. So if it's only about temperature, this could look interesting. The thing that worries me a lot about it is, well, there doesn't seem to be an undo switch. And if you stop and you're gradually getting this back out of your atmosphere, this is why there really isn't an easy undo. What happens is that you tend to get up to not quite the temperature you would have been otherwise, but you tend to have a pretty quick rise, even faster than you would have had originally, to get back near that original set point you would have had, because the world situation is still, you know, getting more and more CO2 into the atmosphere, changing the set point. And if you do that, then you're ending up putting even more pressure on species, and your changes are even more sudden. So that's one of the worries there. But at least people are really studying it hard. So then we get to what I've been working on, and I'll try to zoom through this quickly. In the final lecture of the class, I will go over this a bit more as well, so I can afford to zoom. So this is one climate change effect that I thought was really important to look at. And it's the disappearance of multi-year ice, which tends to be the most reflective over the last 3 decades. And it's disappeared to an astonishing degree. This is satellite imagery by Rigger and Wallace. They were actually looking at the age of the ice, but the age correlates pretty well with the reflectivity of the ice. And the problem that we have is that as it disappears in the summer, these are June to June shots here, in the summer, you take in more and more energy from the summer sun than you would have had back just 3 decades ago. You used to be able to reflect, let's say in loose numbers, 95% of sunlight that would be falling on this highly reflective ice. Now, you know, off this, you're reflecting maybe 5% off very young ice. So it's a real problem, and it contributes right now about 1/3 of global temperature rise. And so it's a big deal. And it's why we have, from the IPCC assessments looking at ice loss, it's why we have this, oh, I never have fixed this darn thing. I added the 2012 info here. This goes through 2007. Basically, what all the IPCC assessments were this range, but what actually happened was this drop off the cliff of ice. And so we've lost about 50% of our area of ice, and we have left about 25% of our volume. So it's not so good. So that's all a positive feedback. So the warmer things get, the faster what remains And when I started this, there was 20% of global temperature rise to this 10 years ago. Now it's 1/3 of global temperature rise. So we have a simple mission. Why don't we look at this as a materials problem and try to put some reflective materials that will allow us to fend off some of that sunlight and try to look for the most benign materials possible. So that's what we've done. And we're applying it to water right now. So we're trying to slow climate-driven ice loss, and we're trying to slow evaporative loss from reservoirs because our drought has come along, and this is a big deal too. And as I say, I'll talk about it more in future, but basically we're floating material or placing material on ice or on water to be able to continue having the reflectivity. And the idea is that eventually we could maybe reboot the multi-year ice in the Arctic, at least in strategic locations, to try to slow this ever hastening positive feedback effect. There are other things it can do. You know, it'll keep things cooler. We could also perhaps prevent the methane release that is another one of these trigger points that's coming at us in climate change. And there is a great value in making reversible changes. This is one of the things I love about Armand's project. It's something that is inherently more reversible than many things that you could think of, and ours is too. You could remove it, you could sink it, you could put soot to undo the effects. Because what we have right now is, you know, think of this as temperature or CO2 uncontrolled, right? Things are spinning out of control. Think of, oh, I don't know, accidentally provoking the next ice age as overcorrecting it in the other direction, right? Oh, the climate models were wrong. Oh, this thing was too effective. But if you have something that you can undo, then you have the ability to carefully and locally tweak things in so that you can tune it to just right, whatever that is. And so we've been working hard on water. We've been working hard on ice. We've been working as a nonprofit. That is one way to make sure that we don't have a profit motive kind of complicating what our motives are. We're just trying to fix the problem. And we've done some field tests, you know, wherever we could get permission to work that seemed really relevant to us. And so we've been around a bit on the getting this tested out. In the water, we're about to move into a really nice pond that actually a landowner is reconstructing for us to make it an ideal test site, which is pretty lovely. And we've got a nice team of folks. This is our test pond in Minnesota with the homeowner and our team there. That's also Minnesota. This is from Barrow, which is right in the Arctic Ocean, you know, abutting the Arctic Ocean. And this is some of our testing up there, what we had up there. And this is sort of where we've been, you know, and we're not in Maine yet. We're thinking about it hard. So these are where we've done some testing just to try to prove out, does this work? And you can do this sort of thing on kind of a shoestring. Although fortunately, we've got enough of a donation now, we're beginning to turn it into a part of our day jobs, which says that now we've developed some of the fundamentals, we can start trying to get it out the door, actually spend daylight hours working on it. And then we can apply the same sort of techniques to water. And it turns out it really works. And we reach a lower temperature, lower peak temperature daily, even in teeny pools. Here is what the pond used to look like with a whole bunch of high school interns and a coworker here. And we were just really getting this thing ready to go. And we're excited about it. We conserve water and we keep lower temperatures, and both of those are great for having drinking water and preserving wildlife. And I could, as you can tell, go on all day, but I won't, because we have Armand. And here is one way to depict you. You get to depict yourself. I will say, as Armand is coming up to take over, and we'll pull up his slides in a second here, this is sort of how I'm viewing the Earth for the purposes of this class, this fragile bubble that we're trying to carefully do something. So as you go through the class, I'm hoping you'll think, what would you carefully try? And we'll see how much time there is for questions at the end. So thank you so much for being here.
Okay, thank you. So thank you for inviting me, Leslie, and to talk about our work. And you know, it's sort of strange. I was at this university as a graduate student 50 years ago, just about this time. I certainly didn't think that 50 years later I'd be speaking here about climate change, actually. So, but anyway, you never know what's going to happen. So this is a project that we started 6-7 years ago at the request from actually people that work with Gates, essentially. This is not the Gates Foundation, but it's a private initiative. And so the people that are on there are, people that have worked with me in my career, or this is a PhD in chemical engineering, this is a PhD in mechanical engineering, and so, we're all in our 60s, 70s, and one of them in his 80s, and so, this between the 4 or 5 of us, we got like 250 years of experience in various fields. Let's see now, make sure I can, okay. So, what is, and why would some people that are basically retired, really start working on this? And in the beginning, this was like a startup. Most of us have gone through a startup and done startups. And so we spent 60 hours working on it, not quite as much anymore. Because, if you see the trajectory of climate change, it's really very, very disturbing. Most have children and grandchildren, and that's really why we're in for that. So, what is geoengineering? Well, you say, it's the deliberate judicial intervention in the climate system. Now, that's a lot easier said than done. In fact, we can't even change, you think about making it rain. It doesn't work most of the time. It works about 50%. In fact, National Academy of Science said you can't predict it. So, at best, it's a stopgap measure, essentially, right? But that doesn't mean it could be extraordinarily useful, okay? And it's certainly not a substitute for decarbonization. So some oil and gas companies like these programs, actually, very much, because they think they can keep on doing what they're doing, but that's not the intent. So what actually happened, why this sort of took up now, Paul Crutzen, Nobel Prize winner for ozone hole, so wrote a paper, planned to write a paper in, I forgot now which magazine. And so this really called a stir. Paul is a very deliberate, very soft-spoken guy, and this coming out saying, now we have to remedy the thing, it's the end of the world. I mean, people are going to believe it. So people actually, tried to convince not to write this, and so when he wrote it, and there was, on the other side, there was why we shouldn't be doing this, as a matter of fact. But, what he really said is, these are all pious thoughts that we have of reducing the carbon. It probably isn't going to happen in time, and that may still be the truth. So why on earth, with all these dangers, what we want to do this, and sort of to describe it in the idea of Eli Kintish, the science writer, is this a bad idea whose time has come? So, maybe it is. So why, if you look at it, so 2015 was the hottest year on record, right? So this is the hottest years over the last that we ever measured. I noticed, I can't quite read them, but all of them are in the 2000 or just close to it, all right? And that was sort of disturbing. And then came, 2016. So by some measures, in March actually, okay, we crushed the thresholds of 1.5 degrees C for a few days. And if you look at it, so you know that in January, in December, we agreed that, all right, in Paris, and that was a very good meeting, so people agreed, all right, we're going to get 2 degrees C for sure, and really we're going to have to, we should really like to have 1.5. Well, 2 months later, before it's even inked, we're there. That's not a good sign. So in February 2016, from what I heard, it actually didn't freeze on the North Pole, okay, this year on New Year's Day. So if you look at it, so for one day there, we had 1.5 degrees C all over the planet, and the northern atmosphere was 2.76 degrees C warmer. This is very, very disturbing. So what are we starting to do? You see these very sad things happening, okay? So if you have the money, like the Swiss, you spend $12 million on duct taping glaciers, right? That's what you do, all right? Well, that's, well, it may lose the glaciers. Maybe that's not the end of the world. But for these people in the Andes, that is the end of the world. And so what they start doing, they're basically whitewashing the tops of the mountains, all right? And whether that's going to work or not. So what you try to do is lower the climate there a little bit so the snow is going to lay. Because, if they don't have the glaciers, there ain't going to be any water in the summer. And that's the end of a lot of the cities along along the back of the Andes. So if you sort of look, and this is the best graph I know, you may know better ones, essentially about 12,000 years ago, we went into this period, the Holocene, right? It's a very benign period. And so before that, we went up and down by 4 or 5 degrees, these various ice ages. But we were lucky enough, essentially, to come over here. And so for these many, many years, essentially, we had that. This is actually made from about 60 proxies, all right? So 3 rings and all that kind of stuff, and carbon dating and all that stuff. So we're sliding into the new coming ice age until we hit the Industrial Revolution and we shoot up. So this is the ice melt in Greenland. You know, what white isn't melting and what red is melting during the summer. And you see that since 2013, you know, it's melting everywhere. Realistically, this isn't the first time that happened. It seems to have happened before. But it's another very disturbing factor. So this is, Leslie is talking about this here. This is the IPC prediction for the ice in the Arctic, okay? And this is where the track that we're on. So we have several of the climate scientists that are working on it, and they have a bet out that by 2020, it's going to be gone in September. Now, it freezes back every year. Used to be 3 meters thick. It's now 50 centimeters thick. So it breaks up much easier because it's much thinner and so on, all that kind of stuff. Everything is sort of going much faster than we thought. And, you know, let me just make a comment on IPCC. You know, it's not that these guys that don't know what they're doing. They're very smart guys. I mean, I'm not a climate scientist. I'm just a simple engineer and physicist or quasi-physicist. But basically, what actually happened, these decisions are made by consensus. So if there's somebody that in Saudi Arabia doesn't like it, they say, you know, that's not acceptable. So they sit there for days or weeks, essentially working on one word. And so that's what happens. You have the ones, you know, that what comes out is common consensus, which is really not a consensus. It's the guy that's the lowest common denominator that's driving it. So this is why this happens. So last week, there was a conference in Oxford of about 1.5 degrees C. So we had the Paris conference, and then people said, well, wait a second, we better take a look at this. So this is sort of convened, okay? And this is not from a, you know, they're all climate scientists and they're observers there. This is a comment from an observer that I got. You know, we're not going to make 1.5 degrees C. There's no way of doing 1.5 degrees C. The only way that we're going to make 1.5 degrees C if we are on war footing, which we're not doing. So if you sort of look what they say, you know, we make 3 degrees C with what we have now, you know, in the Paris Accord. Now the Paris Accords, you know, say that we're going to take 800 gigaton of carbon out of the atmosphere, okay, and put it on the ground somewhere. We don't know yet how to do that, and may require a third of the stuff that we now use for agriculture. You know, this is sort of what's happening, but so anyway, this is the dilemma that we're in. And so you see gradually with all these things there, that if we're going to have to go 2 degrees C, all right, which is sort of the threshold that say you can't go any farther, we probably, sadly, are going to have to do geoengineering. And it's not a pretty picture, but I'm telling you, that's just the way it is. So what we do for this is, you know, the best ones is solar radiation management. It's the same graph that Leslie showed. So you can do this in various ways. You can do this in the stratosphere. You can do this in the troposphere. That's where we're working. And then you can do it on the ground over here, essentially, that Leslie is doing. Now, so you have, you know, there are actually clouds up here, the cirrus clouds, and you would like to remove those. You don't. So we're going to make more clouds, so to speak, but these ones you would like to remove. Because what they're very good at letting light through, but they track infrared radiation, so they're very high. And you know, people are actually seriously looking at this. They're mostly ice clouds, that's why that happens. And so you have to put a bismuth salt in to remove them. But anyway, so these are various ways. So I'm just going to say a little word about static cirrus filter. You know, so this is the Pinatubo option. You know that you saw 1.5 degree there. In 1815, when Napoleon was defeated, you may remember this from that, they couldn't grow any crops actually, all the crops failed worldwide. That was because Mount Tambora exploded, which is much, much louder. And for 2 or 3 years, there was famine all over the world because of that particular explosion. So when Mount Pinatubo put about 20 million tons of sulfur in the stratosphere, and you know, depending on its size, it stays there a couple of years. So you deliver the sulfur here 1 to 2 million tons per year. And you do this very, very gradually. Try to compensate for half the temperature rise. You know, you do this with an airplane, and you spray, doesn't look very pretty, you spray sulfuric acid. And that's very rapidly converted into a sulfate, and you say, well, it's terrible acid rain and all that kind of stuff. It's a small fraction of the stuff, the sulfur that we're already putting out there with the coal plants and all that kind of stuff. So it's maybe less than 1% of that. So the cost is very modest. This is a few $1 billion per year. And there are individuals in the world that can afford to do that. And it's likely to work effectively. So it's unfortunately eminently doable when you think about it. Now, what are the disadvantages? You know, it's difficult to see the public. I don't see anyone sort of joining up and saying, you know, I'm going to go for this, right? It's difficult to do on a small scale. So the stuff we're going to do, we can do this in a little corner of the lab and a little corner of the world. You got to do this all over the world, right? It's going to go up in the stratosphere. It's going to diffuse very, very rapidly. So it can't be undone in a short time. When things go wrong, it's up there for a couple of years. You know, that's what you have. So you know, in sulfur may deplete the ozone layer. You know that we have holes on the holes with the ozone hole are typically around the poles. That's because you have ice crystals there. And so each time you have a crystal or a particle, essentially, that tends to catalyze the reaction of the ozone, essentially, with the CFCs that are there. So you're going to see some unusual effects. You know, you're going to have the sky is going to be a little whiter and all that kind of stuff, essentially. But you know, that's something we're going to work with. So now, to tell you the truth, they're probably going to put sulfur up there. They're working very, very hard to actually find another particle that doesn't do sulfur. But sulfur just happens to be unusually easy to, and so I think they actually have a solution. This is a Harvard crew, and so I think they have another particle which they haven't published yet, and it doesn't catalyze the reaction, but it's probably not nearly as easy to disperse. So marine cloud brightening is something that was invented by a guy when working up at his kids, you know, up in the hills in England, and his son says, you know, wait, look at it, the clouds are like a mirror, and he started thinking about it. So what we do is well, let me just say, 25% of the oceans, right, are covered with what's called marine boundary layer clouds. And you go to the coast over here, that's the kind of cloud that you have. And it's not a very white cloud, okay, and that's because it's typically, it doesn't have any droplets in it. So its reflectivity is on the order of 30%. Now, if something is 95%, you can't do anything about it. You know, you go to 96% by a lot of effort, it doesn't change the reflectivity. But something is 30%, you can do something with it, and it's relatively easy to change. So if you could change that reflectivity by about 6%, which is quite a reasonable number, okay, and you do that worldwide, which is easier said than done, you could change the reflectivity by the order about 1%. Okay, 1% is about 3 watts per square meter. That'd be enough to offset doubling of CO2. Thermally, you don't do anything about anything else, but thermally you could offset the radiation essentially. It was quite impressive. So, you know, you think, well, this is conceptually an environmental design. There is no such thing. You know, all of these things have consequences that we hadn't foreseen. But this is why you have to study it. So our group, we don't advocate that you deploy this. We advocate that you do the research on this, because if you have an emergency, you've got to know what the consequences are going to be if you not have to deploy this. So we're actually, you know, so we're from the very beginning, we knew that we eventually would work with the University of Washington, which has a joint institute for the ocean and the atmosphere. So a little bit of elementary cloud physics. You know, the clouds consist of droplets 10 micron in diameter, right? And say these clouds typically have about 100 droplets of these per cubic centimeter. And so think of the clouds as milk. You know, if I take a glass of milk and dilute it, it doesn't look white. It's the same with this stuff. So I don't know if you're familiar with multiple scattering. So, you know, the more particles, the more surfaces you have, the more reflection, and the whiter it looks, essentially. So these droplets actually form, what you need is a nucleus. If you have a supersaturation, you know, the water will usually condense in the air, but it doesn't make it on the air. It's supersaturation of 400% before you make droplets spontaneously. So that never happens in nature. You know, you have a 0.5% or a small fraction of a percent. So what you need is a nucleus, and that can come from very small hygroscopic salts, so sulfur and sulfate. So where do they come from? Well, so of course over the land we provide lots of them, but over the ocean it's very often from, you have air bubbles that break up, you know, the thing, and so that very thin layer breaks up, and a very few, 20 or 30 on average, essentially manage to escape and go up, essentially. So what happens there then, you know, the warmer air rises, it expands and cools, you have a little bit of oversaturation, 0.5%, and then these, depending on its mass, this thing converts in a droplet for good, and that's it. And that's how you form the clouds. So this is reflectivity, for example. You say, for example, you take, this is the Twomey model, Australian guy that developed this theory and proven out to be very correct. So if you take a cloud that's about 150 meters thick, right, and so, I can't do this very well over here. So you have like, you know, 35, 36%, you double it essentially, you go to 200 particles, okay, you go to 42, you have a 6 or 7% change. That's the way it works, quite simple. So will this work? Well, probably yes. So the ships already, to some degree, do this, right? So the ships burn, why do they do this? Because they burn bunker oil. So we took all the sulfur that we used to put in the gasoline and took it out of it, put it in the bunker oil. Bunker oil is a very, it's very tough stuff. You have to heat it to shove it in the stuff. So you basically a great deal of sulfur that's in there. And so you make sulfates. And so those sulfates do exactly the same stuff. And that's what you see these traces over here of the ships going. This is on the Gulf of Biscayne. This is Spain and Portugal. This is off the coast of California. This is two of the regions where this happens all the time. So it's likely to work. So, and then, so this is sort of rogue science, right? I mean, when we started on this 6, 7 years ago, this was sort of way out and sort of like a really wacky idea. I didn't want to talk about it. And, so we had an article actually in the Economist by Oliver Martin about our thing, and he says, spray and pray. And we believe that Pope Francis is, let's spray. And so we think we're now blessed by papal endorsement, essentially, to go ahead with this stuff, at least the research. So the project started about, there's been 20 years of modeling in this, and so people like to model, essentially, but essentially the rubber hits the road at some time. And so the question is, can you really make the spray that you're talking about, right, in a reasonable way? So I was invited to an Edinburgh conference, essentially, by Pfizer, which is the Gates Funds for Innovative Climate and Research. And so, I was asked to start a project on this here in the valley because, I sort of said yes, not knowing any better. And so that was 7 years of my life that I put into this. So it's mostly a volunteer effort. We had some funds from it in the beginning, and we started about 2009. So what have we done since? Well, we identified 3 methods. One of them very promising, and we don't have a corporate, this is not a corporate structure, scientific experiment. We started with 12 volunteers and about 5 left over, and this is sort of a geriatric crew. If you're not in a hospital or rehab or something like that, we managed to put a few hours working on this, essentially. So that's sort of where we are. And so University of Washington is now formally taking over the project. And we're actually, apart from that, connected to an international group of scientists that are very interested in this and sort of eliminated that. So, I have enormous goodwill and cooperation from numerous outside. So we don't have any funds anymore. So everybody works for free, and I cover the expenses, which are minimal, because we all worked in startup. And so, I got like sheets of diamond, that somebody made for me for exchanging for 2 baldi of boxes of biscotti and stuff like that. So this is the way that we work, actually. So you can't take patents out on this stuff, because you do this, people say, you're in it for the money. That's what you're really doing. And there was this experiment that people started, and one guy had taken out a patent, and all hell broke loose. And so we said, just no patents, period. That's it. So we've gone to 7 conference presentations and 3 article presentations. And so, if you're interested in this, we're very actively interested in young people. We're getting older and older, essentially, and for formal cooperation. So this is a recruiting mission. So what do we want to do? Well, we want to develop a small lab prototype of spray method, suitable for a research ship implementation. Should be easy to scale up. So what we want about 10 to the 15 nuclei per second, So that's a billion times a million. And the salt crystal that we want, 50 to 80, but it can have we really would like to have it in a very narrow distribution. Unfortunately, that doesn't always work. So the energy requirements are secondary at this point, but it should be robust and stable. Now, why does this stuff work? Well, it works because that, so if we make a cloud, right? So I make a cloud, and it's, say, a mile by a mile. That reflects up there at 2.5 gigawatts of power, right? I mean, that's at 1 watt per square meter. So, and it took me only maybe a couple hundred watts to make it, and it stayed there for 3 days, etc. So you get this, 50 to 100 million multiplier in the energy that you put in versus the stuff that you get out. This is why this works. Now, if you're going to try to deal in the same way with ocean acidification, which is a real big problem, you don't have that multiplier. For every molecule that you have there, you're going to have to add another molecule to compensate it. And that's why this is so attractive, and that's why people are looking at this. So the first thing is, some of you may be familiar with this, well, you make some small holes, making small holes now these days with, micro machining, a piece of cake. And that's sort of what I did in my career, at least part-time. And so you make very small holes and you push water through it, it's seawater, right? So we're spraying seawater, right? And it evaporates and it becomes the salt nuclei and they travel up. Or they may stay a droplet, it doesn't matter. It's the amount of salt that you have in it. So you do this, and you put a thing on it, this breaks up perfectly, right? And you actually may have heard that if you take your water nozzles, for a garden nozzle, sometimes you can hear it sing. That's coherent breakup of all those little jets that are out there. So anyway, I did this I was sort of 1971, 45 years ago, I Xerox and made droplets and toner, all exactly the same size. Unfortunately, the holes that you use for this stuff are in the order of 0.5 millimicron and below. And that's very difficult to maintain. Against all expectations, we managed to spray a big bottle, essentially, 50-gallon, through one 5-micron hole. And I was astounded. But basically, so we were quite familiar with all the filtration technology in the semiconductor industry and equipment industry. And so that worked for 5 micron, but for 0.5 micron, we couldn't make it to work. So smarter guys like yourself may do it. This is by far the most efficient way of doing it, energy efficient way of doing it, if you can make it do. So then you think a little harder and you say, all right, how am I going to do this? Okay. So what you do is you take a big jet, so maybe that's one has 20 micron, that's not a piece, that's a piece of cake, keep that open, and I put a big electric field over it, and you pull on it, and what you get is, under the right conditions, you get a very narrow jet coming out. That's called the Taylor instability. And that jet may be 100 to 200 nanometer in diameter. That's exactly what you want. Okay, that's the kind of diameter that you want. And you can do this experiment yourself. You just take a pen and put salt water through it, push a little bit and put a field in, and you see that this works. So this is called electrospray. It's a well-known technique. People have used this before. And the only problem is that from each one of these jets, you get about 10 to the 7 to 10 to the 8 particles. So 10 to the 15, you're going to have to make 10 to the 7 to 10 to the 8 of them, something like that, right? So, they are actually, the particles that come out are very, very monodispersed, as a matter of fact, as it turns out, because they break up very nicely. So how do you do that? Well, I worked at HP, and a lot of guys working with us on this project were from HP. So we would do the same technology. So here is the seawater under pressure. This is very little pressure. So you have a filter over here to put this through. This is like, a 20 micron hole. So this is 100 micron over here or something like that, or whatever it is. So you have a little bit of air pressure because otherwise you're going to have breakdown over here. The field at these tips are enormous. They're millions of volts per centimeter. I mean, much, much higher than atmospheric breakdown usually. You can do that at a very small tip. And so the air blows it through and the particle comes out, and this is an electrode. So this is how you make 100 million of them at the same time. So this is the technology that HP uses. And so what you do is, to make this very thing, you make this out of resist. The only part that there is dry resist. There is no metal. I mean, the metal is just extracting it out, but it's quite inexpensive. So this looks very attractive, except we didn't have the means and the lab essentially to do that. But if you're ever going to deploy it, this would be a good way to come back to it. So then we, we sort of, some of us were in the pharmaceutical industry and said, well, they use this supercritical, processes to, so supercritical seawater, it's basically the stuff that comes out all these fishes in the ocean, right? That's why it's being studied. In fact, by Ken Spitzler, who was the president of this university when I was here, as a matter of fact, and couldn't deal with all the, the war stuff that was going on here at that particular time. But anyway, so fortunately for us, he went back to academics and studied this seawater because the chemistry of this becomes very complicated. It's very easy to get confused, especially for electrical engineers or mechanical engineers. So what you do with this, so you take water, all right, and you heat it under pressure, okay? So, and quite high, 208 in the atmosphere, 370 degrees C, it becomes this gas, all right? But it's sort of like a fluid and it's sort of like a fast. It's super, it's a supercritical water, right? And so the point of it is normally when you evaporate water and get it heated, okay, the salts stay behind. In this particular case, the salt is all in the fluid. So the salt is in that fluid that sort of behaves very easily. And so, that has no surface tension and behaves like a it has gas-like viscosity. So behaves like a gas, should spray like a gas, and lo and behold, that happens. Right? So what you do over here, you feed in your gas here. There's a heater block at the right temperature, et cetera, and out there comes the critical fluid. So you see this over here. So all these pictures, all right, are basically illuminated by white light. So this is the phenomenon of scattering. So the particles are sort of micron, okay? You get white light. That's what you typically have. So you illuminate it on the side with white light, okay? When you actually come in the right range, you have Rayleigh scattering. And so what you see now, the light turns blue. And when it comes very, very small, it's sort of when it works, it virtually disappears because you don't even, the Rayleigh scattering goes down as 6 power of the diameter. So, that sort of works wonderfully well. The only problem is, the only thing that can stand this corrosion is basically diamond and gold. So you take a sapphire nozzle on this and it lasts a quarter of an hour. So the only thing that is that. Critical water is used for extraction of, various things essentially, including fuels. So it's very promising. It's difficult to do. But critical seawater is extraordinarily corrosive in order of magnitude much. So it just can't be done on a reasonable scale. So then we ran to, something I was suggested to us by Purdue University. It's got this effervescent atomization, that big word to saying, that you're mixing water and air, all right, together. So you can do this either by the water in the center and the gas coming in, or you put the gas over there and you get the water coming in, all right? And so it doesn't make much difference. So, but this is the interesting part about it, okay? So normally when you have a nozzle over here, and I'm sure, some of them, you think this is the high pressure, here is a low pressure, right? Unfortunately, this is shifted. You think that you're going to drop all the pressure, okay, over this thing over here, right? That's what normally happens. But when you mix these two together, okay, then you actually have very low velocity, of sound velocity. And what happens, you have choked flow. And in this section over here, the velocity of the medium can't go any faster than the speed of sound. And what happens is that you can't drop the pressure. So when you come out over here, you still have more than half the pressure left over. So here you may have 50 or 100 atmosphere, you have 50 atmosphere left over. So what happens then is that under the right conditions, and of course once you know what you want to go after, you can stimulate it, you make this very thin layer that comes out, just around the surface. And the layer is just a few microns thick. So now I have a layer that's a few microns thick and 50 atmosphere of pressure over there, and it blows apart into very small particles. And that's exactly what you want. So this is a nozzle. This is 200 micron nozzle, and this is 4 or 5 millimeters. So you see enormous rapidly expansion then going forward. And there are 3 trillion particles, droplets, coming out of that nozzle, okay, per second, one single nozzle. So, then you say, wow, this looks wonderful, and so you measure the distribution of this in the air, and, that takes some doing because aerosol is a very tricky field, and so you get the right instrumentation, and wow, under some conditions, you get a perfectly log normal distribution. Problem solved. This is exactly what we need now. Well, there's only one problem. It's an almost log normal distribution. And so this tail goes out over here, and it goes on and on, very, very low. But unfortunately, it goes like the third power. So what you have is almost 90% of the mass is over here, and 10% of the mass is over there. So you're not spraying very efficiently. It's good enough, actually, to do the experiment, but it's not necessarily the most efficient system. So we've now been playing around this for, gosh, a year and a half. Time flies when you're having fun. And so we now have systems that on occasion do 4 times better, actually, than that, with very simple means. So it's ready for action. So what would we like to do? We like to build a prototype now, and sort of, this is in the lab. We spray this in the lab. We measure it in the lab, okay? Seems fine. So what you get is you buy one of, you get an old one of these, snow launchers, snow makers, right? And so that's got a couple hundred, we need about 300 nozzles essentially that you put in over here. That's how a snow maker is made essentially, right? And so then you put a big fan on it, and this is what happens. So you throw this up in the air. But the particles that we're throwing up are 1,000 times smaller than the ones you have in the snowmaker. That's the difference, right? So you would like to do this on in sea, that's where you're going to do that, but it's much cheaper to do this on land. So we do this somewhere near Monterey, and so you get a few of these trucks over here, and so what you put on there is you take off this snowblower that you have there, and you put a cubic meter of seawater, and you put in your compressor. All the energy goes in compressing the air, essentially. And then you have a diesel generator in the back, and you now have a mobile unit that costs 1/100 of the experiments that you do on a ship. And as long as you have an influx of maritime air, the experiment is much easier to do. So that's what we're working to now, and that's what we're looking for funds for. So what are the applications of this marine cloud brightening? All right, well, it's a great tool for cloud studies, okay? Clouds are the largest stone known in the climate studies, right? So some models come up with 2 and others come up with 4. Well, the difference between 2 and 4 is dramatic. 2 will probably do well, prosper is something else, but 4, according to the World Bank, and they have courses on this, by the way, that you can look up on the World Bank Coursera, you can't have an organized society as we have. We'll survive, but it ain't going to be very pretty. So this is why it's very important to know this is the first time that people, you have cloud chambers and all that kind of stuff where they do this in laboratory. But this is real life. This is enough nuclei that 4 or 5 of them, you can do this essentially and follow the nuclei as they go and you can measure this with airplanes and all that kind of stuff. So that's half our intention. And so, what else could you do? Well, along the coast of California, as a graduate student here in the 60s, I would wake up every morning and, it'd be 60 degrees C and be cloudy, and that's what it was. And then by 11 o'clock, the clouds would break up, essentially, and sort of get to 75, and then every day the same. So one day I remember in September, it went to 91 degrees C, Fahrenheit. And people thought, that the world is coming to an end. I mean, we were not prepared for this stuff. Well, it's no longer the same. Where I live in Portola Valley, the clouds are gone every day, and most I'd see in the valley over here. Our climate has changed, and so the redwoods know that, and they're actually straining very hard. So they don't have the fog anymore that used to come, and they're really straining to the king. So, this would be a perfect way to do an experiment. You don't need very much. There's California coast, essentially. You have the right marine boundary layers and all that kind of stuff. Of course, protecting the Arctic region is probably number 1, if you can do it. You could decrease maybe hurricane intensity, and all of these things are a little dicey to put it through, but they should be tried. So when Hurricane Katrina came in, and whatever it was 10 years ago, it sort of brushed on southern Florida, right? And it was a Category 3. Then it went over the Gulf of Mexico, which is 5 degrees Fahrenheit, warmer than usual, and that's where it picked up all this energy. And so when it landed in New Orleans, it was Category 5. So if you would manage in the places where this happens to keep the temperature of the ocean down, okay, that would be great. You could knock off 1 or maybe 1.5 essentially from the categories. So control of El Nino, so Ken Caldera and students here at Stanford have been working on this essentially, and it actually look quite interesting. So you could try to protect the coral reefs, and then you might look at global temperature reduction. At each time, there's sort of 50,000 large ships on the ocean. And if you give 4 or 5 of them of these sprayers, which might cost a couple $100,000, that gets lost in the noise, you could actually make an impact. So if it actually works. So as again I'm saying, I'm not advocating this essentially. Now, are there adverse effects? Well, you can stop this in 2 days, 2-3 days, the clouds are gone. But of course, if you've been doing this for years and you stop it, you're going to have some consequences. There's no question about it. So you might have increased droughts, etc. And so the only problem is, so some say yes, some say no. The problem is that the climate models, the precipitation is by and large the most thing that is dubious, the outcome, that they cannot predict with stuff. So this is just a final slide, or a next to final slide. That in my opinion, there is no planet B. I know that Elon Musk today is in Guadalajara and telling us that he's going to colonize, and all that stuff. This is all fine and dandy, but I think those billions would be much better spent on our own planet, essentially, than doing Mars. I mean, I have great respect for him, but people can go wrong. Yeah, and if you look at it, so this is a picture from Voyager 1 that was taken. Carl Sagan asked them to flip their cameras and looking towards the sun again, and they managed to take this picture. We're sort of all alone there in the universe on our own. I mean, and we're very, very vulnerable. If you look at this for over here, so this is another one from the spatial So this is the Earth over here, and it looks infinite in this direction. And then you have the troposphere here, and then you have the stratosphere, and then the ionosphere. This is very, very thin, okay? So if you take all the air that's there and you compress it, you got 7 kilometers. If you make it liquid, so to speak, by liquefying it, okay, now you have 7 meters, a factor of 1,000 in density, okay? If you take all the ice that is on Greenland and you melt it, you would have the same amount of liquids than you have from all the air that's up there. And if you just think about it, so the ozone hole, big hole, why we have lots of ozone. You take all the ozone that's up there and you compress it, you have 3 millimeters, 1/8 of an inch. That's the thickness of the ozone layer. And somebody actually in President's Lab discovered in 1967 that you take 20 tons of bromine, okay, and let it up go. We're through with the ozone layer. That's it. And it goes much faster than with chlorine. And we almost brominated the CFCs, okay, instead of chlorinated. But it was fortunately for us, a few cents more expensive. So it didn't happen. But we would have lost the ozone layer, okay, before we knew what was going on. So anyway, these are our final thoughts. We're now in an area of consequences, as Winston Churchill said. And so it's up to us whether we're going to, keep our seat first class on the Titanic, or we're going to change course. And so our future isn't predetermined, and certainly not without hope. And geoengineering may or may not be, help us, but we certainly should do the research because it's very high time to do this. So anyway, and so if any one of you is listed, I'd be delighted to talk to you and see if you can help us one way or the other. Thank you.